My pleasure to introduce Jason Tichy from NVIDIA. He is a senior solutions architect. He brings a deep aerospace background. He formerly worked at Aerospace Corporation and NASA Goddard. He's an expert in GPU-enabled machine learning and teaches a number of courses on the topic, some of which you can find on YouTube if you're curious. Brings extensive knowledge in high-performance computing-enabled video and image processing pipelines and a valuable industry-scale perspective to the workshop. Join me in welcoming him.
Thank you. Microphone's on. Everybody hear me? All right. This will probably seem kind of like a brief overview of the three other presentations we've had, just because I get to go last, and that's how that goes. So everything we're talking about here today is data, and it's not just space that's exploding in data. The entire world is exploding in data. Hard drives are becoming super cheap. We now talk about laptops and how many terabytes we have. I remember buying my first 60 megabyte hard drive way back in 1992. But it's a term that just keeps blowing up, and we keep finding more and more ways to use our gigantic data. And so, just a point, the world as a whole is expected that, by 2025, you're generating 1.75 megabytes per person per second, which is just insane to think about. People keep doing that to themselves. What does that look like today? And this is a little bit of older data where they were projecting, but this is how much data the world collects each year. And so this year we're looking at like 44 zettabytes, and there's no way that compute has been able to keep up with processing. The cloud exists because we have to rent computers now instead of being able to afford our own. And this just keeps going. And to bring it back to a little bit of NASA specific, this is off of a page for the Earth observation satellite data where they're predicting resources that they need in 2025, and they're justifying their move to the cloud. And we're here at this workshop to propose solutions, and the cloud is a great solution. But I like to highlight a note from the article that NASA is choosing to move to the cloud because they're hoping once the data gets to the cloud, it doesn't have to move again. Moving the data is completely suboptimal these days. If you can compute in place and never move the data, you can get a lot more done. And so NASA is looking at the cloud, but that's even after we get it back down here to the ground. Admittedly, these slides, follow the last talk as a brief. Let me see if I can understand how the DSN works from an industry's perspective. So here we have, my wonderful visualization of JWST, and if I understand correct, if I want to do research on JWST data, images coming in, I've got to wait for the spacecraft to communicate with the DSN network, whether that be through relay or through the dishes on the ground. But that is a back and forth communication that has to happen. And then that goes, there's that pipe that he showed in the last that, you have the ground system and the scientists that get the data, that they have to go through the DSN. And then, hopefully then we're at a system now where I know for a fact that the ground system uploads their scientific data to the cloud for processing. I'm not quite sure. Maybe somebody can educate me. Can the DSN just dump to the cloud?
We can, but we don't.
You can, but security, right? Okay, yeah. So that's a pipeline I hope exists first. And so we're here today to talk about the future of computing. But what I want to do is kind of pat the world on the back for how far we've come. With the help of the cloud and the current system, we're able to do amazing things with Earth's, vital data, looking at global warming and filling in the blanks. You can use the cloud and artificial intelligence to fill in the bits between the pixels that you couldn't quite get from the spacecraft. And it's really exploding. With the cloud and what we do, we're able to see gravity and black holes and all sorts of cool things, and also, design future missions. And the cloud is great. And so I say all of that just to kind of say, hey, we're killing it, but, in the future, we need to figure out how to intermingle that. The cloud told us that HPC is the way to go, that you don't move the data around, you don't want to copy the data to your home computer and then, wait for your MATLAB license to spin up for the day and, curse when everybody's already taken up the day's MATLAB licenses. If you could just do it all in the cloud, you no longer have to have the license fight and everything else. So HPC is helping bring new ways of applying this data. And since 2012, we have exploded in applying artificial intelligence to help us go through a tremendous amount of data in a way that has both helped but has both hurt. Like with AI, we need more and more data in order to help us reduce how much data we need. Does that sound a little backwards? Because it's kind of true. You have to train with massive amounts of data your AI. And then, in the future, we can talk about loading up AI to the Mars rover so the Mars rover can do things like track dust devils and other things. But HPC is kind of enabling that. But, we need to move to the sky. And this is kind of my closeout before moving it over to Dr. Lukas Mandrake, who will be talking about, moving it from the edge, and how do we move towards a world of autonomy and having the spacecraft do their own compute. And so this almost is a great summary of everything we've heard today from the other three talks, and that is bandwidth is extremely limited. The DSN only has so much they can do with the power and everything. And, I looked up on Wikipedia. It took 469 days to get that New Horizons Pluto flyby data. I don't know if that's exactly right, but it's Wikipedia. Pure latency, light time. There's just too much time between us and Mars and us and any other planets in the solar system that, if you see something interesting, it's gone the next time you have communication with your spacecraft and you don't know how to go find it again. So time critical, having compute out at the spacecraft helps solve that latency problem where you can have your algorithms running out there and bring back results rather than bring back data and availability. So with that, I will close out and introduce Dr. Lukas Mandrake, who will be talking about bringing autonomy.
I want to talk right now about autonomy. You've heard the need for this entire time. So what the heck is it? What does it look like? What are some of the things that it could do? And what are the wrong ways to use it and the right ways to do it? Because in the end, we're serving scientists. Missions are launched because scientists have questions. The data is gathered because they have questions. The data is analyzed by the scientists, and they tell us if the mission was worth it or not. So all the autonomy should really be in that framework. Getting in the way of the scientist is the last and worst thing you'll ever do if you want to work in this field. All right. And it should be that way. So when to use autonomy, a super fast overview. Anytime your reaction time isn't fast enough for the information to go where it needs to go for the thinker and come back so that you can actually do something. If that's true, you have to use autonomy. If it isn't true, don't use autonomy. Just have a human do it. Anytime you gather so much data that you just can't get enough humans to actually analyze it all, you can't store it all in real time, so you have to actually process it and dump it. You don't have enough compute to process it to begin with, or you can't shove it through a pipeline where it's going. If any of those four conditions are happening, you probably need autonomy. If none of them are happening, you don't need autonomy. So I am not here to tell anybody autonomy everything, because guess what? Humans do everything better. There's just not enough of us, and we get bored. Those are the two main problems. All right, so where have we already used autonomy in the RNTD at JPL, and actually in some flight missions already, though very small scale ones, and we're seeking to increase that. This is the data life cycle of science data at JPL. It also happens to talk about the telemetry from the spacecraft, and we'll get to that later. But you come up with the concept of the question you want to answer, you get the data, you transport it to somewhere where you can actually handle it. The operations people receive it, and they're trying to figure out, is this good or bad? Do I need to change something about the acquisition in real time? Then you try to calibrate it. You put it in a place where everybody can get it together with the metadata to analyze it. You quality assess it. You analyze it. Finally, hopefully, you extract some knowledge out of it. And then you put it all away so someone else can write papers about it later on other than you. All the lighter bars on this is where we've applied concepts of autonomy to help something at JPL. And autonomy can mean many things. In my context, autonomy does not mean a small lifelike object which is trying to think and survive on another planet and decide what to do. That is absolutely not autonomy. That's called life. And we're not trying to create life. Instead, autonomy can be seen as a quick advisory loop. I don't have time to ask the human scientist, does this matter or not? So I'm going to make a quick approximations to that. Because I talked with scientists for a while and tried to learn what they were telling me, these are not going to be high fidelity decisions. They could get pretty good, but it's this quick look that gives you insight early on so that you can make better decisions than if you had no insight, which is what the current spacecraft have. Absolutely no idea what they're doing or why. All right, so at JPL at least, and in the space community everywhere, there's three main operational frameworks that we tend to think about when we think about autonomy. The funny thing is, the technology for all these different things I'm going to talk about are exactly the same. The algorithms that we write from the data science point of view are almost indistinguishable. But the implementations of the algorithm look radically different depending on where they're going. The first one is archival and ground. This also shows the history of data science as we're growing as well, and you can see where we're going. So on the ground, you have massive data sets, terabytes of data sets nowadays. But you have cloud computing. You have GPUs. You have all the compute you could possibly want up to the limits of your local power supply. The data volume is also immensely high, and that's a challenge. But the data velocity is low. Like if you analyze this data set, you don't need to constantly have new data sets streaming into it to get an answer. There's a lot of information. You can look at this right now. So sit down, spend 3 months, use the cloud on it, write fancy algorithms, and then try to publish your paper in your knowledge extraction. So what are the areas where autonomy can help here? Now, there's one autonomous system that everybody in the world pretty much has now experienced and even done machine learning-based training on, is your spam filter. That is a fully autonomous system that's trying to make a prediction of whether you should even be shown this email or not. And you get to say yes or no and train your classifier. Watch it fail because you added this company to there and now it got rid of your friend. Oh, it's because there's commonality in the text. All that stuff. So everybody knows about that. And that's really kind of what's going on here in the science data campaign, except the science data is vastly more complex than email. So anomaly detection. I don't want to know what I'm looking for. I want you to show me bunches of normal stuff you don't care about, and I'll show you things not like that. That's the general anomaly detection case. Focus of attention. I don't know where to even start looking in this data. Could you please show me a representative sampling of the things that are in this data so that I can quickly look through that and zoom in on what I want to study? Context-based search. I want dunes. I'm a dune scientist. I want all the high-res images with dunes, and I do not want to see images without the dunes. It does not need to be a perfect dune definition. It does not need to be 100% accurate. Just please don't show me things with no dunes, and if it's confusing, I'll take it, because I'll be able to say no later on. Quality estimation, should I even be looking at it, or is this useless data? Exploration and mining. Interactivity appears here enormously. I don't want you to tell me the answer to my question. I want you to give me a best guess, and then let me say not that, not that, not that, and then give me a better guess. So you're using the tool almost like a human-robot interaction to help drill down on where you're going. And then finally, active validation and verification, which is really everything in data science can go in there as well. These dark regions are how powerful it is in the archive and ground configuration to do that. And you see the dark blue over here means they also apply something to the right. Finally, there's change detection, looking for things that change. This is a special application we'll talk more about later. But if I'm looking at an image, it doesn't tell me anything about change unless I look at the same image again acquired later. So now you're deltaing and differencing your data to get the information out of it, kind of like taking a derivative. And then finally, there's use cases down here that have nothing to do with the archive on the ground. But over here, they do. Now we're on board the spacecraft. You have no compute whatsoever, really. I mean, it's pathetic what we have in space right now. That's why HPSC matters so much. You have kind of like a cell phone from 10 to 20 years ago up in space right now. You can't run your favorite programs on these spacecraft, and then we have to do science extraction. But yet, out there, you have the most stringent requirements. Should I or should I not send this back home? I want to do change detection, but I can't store the images. They're actually too big. How do you even do that? I want to compress the knowledge in the signal, but not just information compression with a zip. I want to compress what was there. What did I see? And then super high resolution zoom-ins on the things of interest so the scientists have the actual raw data, but only around where there was a hint of something to look at. So the applications of the technology become very, very different when you're out here in space. But in the end, these are all the same machine learning and data-driven analysis technologies that you see everywhere. And then, of course, we have the intermediate case. I'm sitting in ops. The data's flooding down. It's real time. I need to quickly assess, is the rover in danger? Is one of the instruments going out of calibration? Or is the fact I'm looking at a cloudy image actually a scientific discovery? That's the case of ops, where you still have the cloud, all the compute you want. The data volume is not so bad. It's the last day or two. But the velocity is streaming through, and you have real-time requirements to make these decisions. And so now you start talking about some of these, but there's a lot of context-based information that I need. I'm looking at the data, and I want all images that looked like this at this time, looking at a rock like this, so I can do that comparison. Where are all the papers on this, and who is operating on the last day an error like this happened? Because maybe I should talk with them and see how they resolved it. So constant focus of attention. All right, so those are the three main contexts. Now, let's actually walk through the linkage. And you've seen a graph kind of like this before, but I think I'm going to put a slightly different spin on it. So autonomy really is just the march of the same old data analysis that we've always done on the ground with humans, pushing it more and more up the stream to the concept that's now called edge computing. We used to just call it out there. There's a huge disadvantage. Everything is easier on the ground. Humans are the best computer we have to analyze data of all. And if you can put them in the loop, everything goes faster and better. The pro is that there are unique opportunities out there if you get those early insights, things maybe you couldn't even ship down. So right now, this is where we live. It's called the in-the-loop model. Discovery and exploration, these are the scientists sitting, processing their data, trying to figure out if the whole thing mattered or not. Then planning and operations, these are the people trying to decide what's actually going on. Humans are fully in control. This is where you live roughly right now. And we have autonomy solutions in place down here that help people explore the data and look. Up here, you start getting into smart instruments. The camera doesn't take a picture. It takes a picture, and it sees if everyone's faces, which is identified, are there, and tells if their eyes are open and if they're smiling, and then helped take some additional pictures in various cases and stitch the faces together to get one composite image with everyone's eyes open and they're all smiling. The raw data is also given to you, but so is this composite image upon which we can decide the quality of the image that you're downlinking. That's actually something that just everybody gets in cameras nowadays, a fully autonomous system. You can do it with space data too. Now, reactive observatories. I'm an entire system, like we'll talk about MRO around Mars because of the excellent introduction. And there's two cameras on there, a context camera that looks at lower resolution over a wide area, and then a very high resolution, Highrise camera that can take very fine spatial detail, but you can't downlink all of that. So you could have a detector running in the wide swath informing the higher resolution one when to take an image, for instance. Finally, we get to collaborative observatories. Maybe I want to put a swarm up there, and they're all doing their different science, but then every once in a while, one of them says, I detect something that's not really what I can look at, but you can, and it tells the other one to retask and look over there and gather that in an opportunistic fashion. And then finally, this is kind of like the dream upon dreams. By the way, this entire thing is called now humans on the loop. Did I ever say that this was going on without humans present? That's ludicrous. We're talking with them every few days. We're updating their weights. If the autonomous systems do something we don't like, you tweak them with new data, you upload those weights, and now they're behaving better. Humans are around. We're just not holding their hand all the time. It's more like going to office hours. So that's called human on the loop. And the last part of the stream is cross-generational collaboration. I have 4 assets already on Mars, and a new one shows up. And the old ones now do better stuff because the new one's there, as well as the new one doing its own stuff. That's really sophisticated and advanced. So never ever did I say the words fire and forget. This is a very dangerous concept. We don't have the technology to even think about that. You would need to be able to think. And no kind of autonomy can get close to thinking right now. They're just statistical probes. All right, so I'm going to give you a whirlwind tour of some actual autonomy that we built that worked. I'm not going to show you the ones that didn't. And then I'm going to go into one of our initiatives that I think is, well, it was already introduced a bit, the Cosmic project, that is the most state-of-the-art advanced application of autonomy that we've attempted so far. So an early warning system. Although it applies to nuclear missiles, I'm going to talk to you about it in terms of wonderful science instead. There are all-sky surveys that happen every single day. They look at the night and they take a picture of the entire sky. They have reference images that they subtract off from that. And the whole point of this is the sky's not static. Things change all the time. Wouldn't it be nice to know where all those things are? Among the many things that change in the sky, one of them, every once in a while, exceptionally rarely, is a supernova. And supernovas are very funny. A star slightly gets brighter, or a star appears where there wasn't one before, day one. On day two, it reaches peak brightness and becomes something that if several observatories on the planet were all oriented to look at it, you actually now have a standard candle that is measuring information about cosmology that is completely unique and cannot be obtained any other way currently. On day three, it's fading, and the ability to determine assignments from it is gone. So you have one night, maybe two if you're lucky, to predict that it's going to be a supernova on the third night. The problem is it has about 200 million detections every night of possible change, and the suffering grad students can only look at about 200 every night to decide which ones are worthy of following up on. This system does not find supernova. This is the key. It finds not supernova. It tries to find not supernova with extremely high accuracy, but in the end, it only gets down to about 200 top candidates and does not try to determine if it's a supernova after that. All we did is down select the highest priority data for a human to look at, but the humans are on the loop. They're in control. And they can deweight it and change it tomorrow if they don't like what it did. So of course, this is one of those situations where think about the fidelity of accuracy to go from 200 million to only 200, and yet I did not make a supernova detector. That's a harder problem. The average NG hyperspectral information that we have right now, this actually was David Thompson participated in this along with Brian Bew. But we have beautiful hyperspectral imagers. They take pictures in thousands of colors simultaneously, so you get an entire high-resolution spectra while you also get beautiful pictures. What's not to love about this data set, except that every picture you take is a three-dimensional data cube, and every movie you make is now a four-dimensional basic object. So a human can't even look at the image. They have to sit down for about an hour to look at the image in all possible ways, zooming what RGB means up and down the stack to figure out what one thing means. And yet, if you put it on a plane and fly it around, and you have the right kind of classification technology tuned on it, you can see invisible gases coming out of the ground like methane, say that are buried under the ground 12 feet down where no one can see them, away from a road and away from all power lines, but that is leaking millions of dollars of methane into the atmosphere. Bad for the company, bad for the environment. And that's exactly what they did. Created a technology that allows you to spectrally find the associated methane, spatially gather that together into a proposed plume, estimate its probability, and then in real time, with advanced autonomy that was squeezed down to run on a desktop computer stuck in the back of the aircraft, it would be able to tell the pilot and the scientist, call in the ground teams, I see something that looks like a live plume, it's happening right now. If they turn the pipe off for today, you won't see it anymore. The pipes turn on and off all the time. So then the ground teams rush out with their special camera that can see it, and there it is, leaking out of the ground, and they actually found this. There's pretty much no other way to find this very well. This is an instrument that is one of my most exciting ones. We're working on it right now. It's the OWLS project, Ocean World's Life Surveyor, and this is one of the rare cases where an instrument that was just starting to be built came to us and said, hey, we think we need autonomy. Let's talk as we build the instrument. You can work on our crappy data as it's coming out, which we change every month and causes you headaches. But at the same time, you can then give feedback to us on what our data should look like to allow the autonomy. So what this instrument is it actually has a mass spectrometer on it, and then it has a digital holographic microscope that sucks in liquid samples, and then in that image, there's hopefully critters moving around, and it's at every time step, it's taking a holographic image of that little volume. That's what you're seeing right here. This is actually a time movie. There's little pixels changing, and there's things that aren't moving, and there actually are things that are swimming around too. But is this a very pretty picture to look at? Right? This is a nightmare because it's actually a raw digital hologram that's been smashed into 2D. It's not the normal space that we look in, though you can see things underneath it. Humans can label what's moving very, very easily because all you got to do is imagine it's dirty ice and there's things swimming under it, and the ancient parts of our brain that find things you might eat kick in, and you can immediately say, oh, there's the creatures. But detection and tracking systems can't handle this at all. So with the humans, we label it, and we use machine learning to create detection and tracking systems that can. And here's the reason why. When this instrument is built, it can plunk down on Europa. It can take a scrape out of one of those pieces of ice that just welled up. It can melt that, and then it can say, is anything moving like life? Now, would you like to sit down and write the 24 instructions on how to determine if something's moving like life or not? Nobody can. But I can have you label the data very easily and then use machine learning to create a statistical model that actually does it with extremely high fidelity. The instrument generates about 2.5 gigabytes per second of data. You can downlink 70 megabytes at the end of the mission. So this is an extreme data triage case. Also, most of your samples will be barren. It's very unlikely that anything is still living by the time it upwells. So there might only be 1 or 2 needles in a haystack to look for. That's the sort of thing that this is useful. Barefoot Rover. Imagine if one of the rover wheels actually had sensors wrapped around it and it's rolling on the surface of Mars as it goes. So for free, you're getting a camera that images the surface by touch. Now imagine if you could close your eyes, take your feet off, and just walk around in here. You'd find these. You describe that they're square shapes and probably even what they're made of based on temperature. It's actually a really interesting thing if you turn the lights off, take your shoes off, and see what you can learn. That's the sort of thing that this could do, including terramechanic properties of the soil. And all you have to do is wrap a sensor pad around it and process it on board. It generates too much data. It will get in the scientist's way. But if you send reports back, I think I found this, I think I understand, I think I found this. And by the way, there was a big change when I went from here to here. These are hints that you just crossed a geologic contact point in the terrain. That's exciting to scientists and might not be visually apparent based just on the engineering orientation cameras that are normally firing. All right, this is one of our most famous ones. It's been on Mars for quite a while. Started with the MER rovers, now it's on MSL, and it has plans to go to Mars 2020. We, of course, as you all know, took a robot, put a laser on it, and invaded Mars. We got it wrong a little bit in the past stories. And what this laser does is that when you shoot a rock, it explodes with a puff of plasma, and by looking at the color and the spectra of the plasma, you can tell what that rock must have been made of at a distance. Is that the coolest sensor or what? Active remote scanning. However, the process of using this was the rover drives for a day, and then it stops. And it's about to have the sun set, so it can't do any more science. So it takes a picture, it uploads it to Earth, and it goes to sleep. All night, all the Martian night long, humans frantically work on that image, and they select all the places you'd like to shoot that rock, shoot the laser to measure the rocks around you. And they upload those commands, so when it wakes up in the morning, it takes its data, and then continues roving and repeats the cycle. Cool. That's the normal cycle. But what about if at the end of the day, it goes to a new place, it stops, and then it looks around, takes the images, and decides what's a representative sampling of the different rocks of the kinds that scientists typically like me to measure? That means you have to autonomously discover what a rock is, which turns out is incredibly hard when there's shadows and irregularity. There's really almost no assumptions you can make. Humans are great at it, so we're confused at how hard this is. And then it takes that data as a representative sample. Notice I didn't say it images the important rocks or it does science. It does not upload a paper at the end. But when you get that image to do your selection, you already have a representative spectral sampling of the rocks around you. So the scientists can get to the important questions with more informed context. This is beautiful autonomy because it informed scientists to do their job. It did not attempt to do their job. Lastly, I want to touch on these little vignettes I'm showing you. Telemetry. Why am I showing you telemetry? We're all scientists. We like that. Because telemetry is becoming science data. When I was working on OCO2, the CO2 we were measuring out of the atmosphere as the mission was going around the Earth would occasionally get a little crazy. Obviously crazy. Physically impossible values were coming out. What's going wrong? We did correlation studies, everything else. I started using some machine learning on it and discovered it's correlating with things that seem to be more instrument parameters, more hardware parameters than anything in the atmosphere itself. It was almost impossible to extract from the telemetry anything coordinated with the observations. They're just not even aligned or stored in the same formats the same way. And it turned out it was because one part of the CCD was occasionally getting a little bit too warm, and there was a thermometer in there that was telling you this, but people just didn't bring it together. So now imagine on the GRACE follow-on mission, where the instrument are two spaceships pointed at each other with a microwave lock between them, and they're measuring that distance extremely finely as they go forward and backward over high density regions. The spacecraft and its telemetry is the science data. You take a derivative of that to get the science data out of it. So as we go forward, you can't really distinguish, oh, this is pure for science, this is pure for telemetry. Don't look at each other. In this case, the OnWatch system says, right now, when you downlink telemetry, they say, we only need this once a second, we need this once every 5 seconds, oh, we need fine resolution on that. But what if the anomaly that happened on board isn't in that scale? Shouldn't it be building a model of itself and its normal operating parameters? And when it senses something's happening I've never seen before, it just bumps up the collection rate to make sure that you get the best answer on the ground to figure out what went wrong. In fact, while we were working on the GRACE follow-on anomaly, they said if it's even in the telemetry, which was not very encouraging for a data scientist to be looking in the data to resolve the anomaly. All right, so let's pause for just a moment. That was a whirlwind tour. I know it was a lot. I'm going to do a slightly deeper dive, and then we'll be done on the COSMIC mission, the COSMIC project. It's in its third year of 3 years as a strategic initiative. And this is one of our flagship missions in the data science area of what you can do with autonomy. Content-based onboard summarization to monitor infrequent change. I want to call out some points from the previous speakers today, live edit talk from Valerie Fox. Bias in the data selected is of key concern. Anytime you have autonomy, picking the data the scientists get to see, that's a really big concern because you could get them to say anything if you just filter the data they're allowed and not to see. Of course, we also have to acknowledge that the scientists themselves were imposing their bias on it. Bias is good when it's informed. Bias is bad when it's mistaken. But the whole point of exploring a planet is we're not fully informed. So bias is just tricky all around. It's very easy to get it wrong. It's almost impossible to get it right. But as an autonomy person, you must be willing to stare very carefully and see, am I messing anybody up? Statistical sampling matters. However, it's also easy to miss spontaneous and transient observations. They're the ones you can't tell the spacecraft what to do or where to look for or where to target. Now, especially if that's the science of interest, you're kind of in a mess. And then, of course, there's improved spacecraft computation that's coming. But this is reversing how we normally do these missions. Usually, the scientists say what we study. We design a spacecraft, an instrument suite that barely answers the question needed for the smallest amount of money because it's a competitive process. We fly it up there with the minimum compute necessary to gather that data, and we return it to Earth without thinking, hoping once it's there, then the scientists can take over and see if it works. However, now that we're thinking about putting autonomy on board, well, initially they were like, yeah, you can do that in phase E when we've already done our third extended mission. And so in case you blow the system up, and we were always like, where's the command to blow the spacecraft up? We never did find that. But, so we are told you have to run on a tiny pocket computer. We are told that you have to compute in 1 hour or you'll get in the way of our power management system. That is always as it has been. Now they're coming to us and saying, I'm sorry, exactly 21 or 24 bits is that you need the depth of the computer that it can operate for your algorithm. Excuse me? I haven't even written the algorithm yet. I'm writing a proposal, and you're trying to optimize the bit depth of your future computing system. There's a lot of strange questions that are starting to flow back our way. How much heat does it take to find a dune on Mars? Oh my God, like I need to answer that before I can get the money to make the algorithm to find the dune. It's pretty tricky. All right, so beautiful introduction. Previously the Highrise instrument on MRO. It's quite honestly my favorite instrument in the entire solar system right now. It gets you back stuff like this, right? And let's be completely frank. Every one of these was targeted by a scientist. That's the point. They know what they're doing. Look at the stuff that they actually got back. And what happens when you see at a finer resolution anywhere in nature at any time ever? You immediately see more complexity and you have more questions than you actually had a moment ago. In fact, almost all advances in science come from being able to see better. Everything else is trying to make sense of the facts afterwards. But we now can see so finely. I mean, look at these structures, the black coming off of a dune and all this stuff. You can only downlink about 4% of the planet in about 6 years. There's no way that you will understand all of Mars with an instrument that's that bandwidth constrained. So target, target, target. What do you want to see? We are not just going to march in a little chain and see how far we get, but let's use all the knowledge we have to predict where we should even bother looking. And here's the current mode of how we do that. So scientists know what's interesting in the questions that they have. They send commands through the DSN over to the spacecraft. It takes the data. It flows back ever so painfully and slowly to Earth, and then they see what they see, and they ask for the next set. This is how we went to the moon. This is how we figured out almost how the entire solar system works, cosmology. It actually is pretty darn good. That doesn't need fixing. Unless the target doesn't stay put, unless it's transient, and unless I can't target it. Or if I don't even know it's there and you stumble upon it, wouldn't it have been nice for the rover to know that? So change detection is where it's at. This is a simple overview of just some of the functionalities. I'm not going to talk about how we achieved it or anything like that. But for the cosmic system, what if you had a future MRO where the Highrise camera could just be left on? Every photon streams into that camera and is analyzed by the onboard compute, which is much larger than it is right now. The current MRO, the current Highrise can't do this. The camera would overheat and melt itself into slag if you try to do this. But with a small engineering tweak, you could get around that. Now, some areas, the scientists who say, I want you to monitor this high resolution region, I can actually store those pixels on board, not send them to Earth. The next time I'm overhead, I can take the same pixels, align them very, very carefully. That's harder than it seems. And then I can do direct change comparison on the pixels, the way everybody thinks about. But I don't send anything to Earth until something changes. That's the key. So you could have tens of thousands of places on Mars being watched that only send an alert back to Earth when something changes, and even in the way that you define the change of interest. That's an advance. But let's get wilder. There are some kinds of landforms. This is a particularly weird one, where actually there was a fresh impact that had the side of a crater, and then an RSL flowed out of the crater afterwards. So that's about the most transient thing you could ever get. These, if you see these on the surface, this apparent blast mark, which is just dust being cleared over a darker surface, blows away very quickly. The dust comes and fills it back in with the winds. So the fact you're seeing this means it's transient. Just like if you see a still image of someone running, it's indicative of a transient event happening. So Cosmic also has the ability to have a library uploaded to it of these are the things I'm looking for. And if it sees things like that, then it sends an alert back. I keep saying the word alert. What's in these alerts? What did I see? Why did I think it was useful? Here's some summary information about it. No pixel, or maybe a tiny thumbnail of just to give you some indication. And that goes back to Earth, almost no bandwidth. It's still the scientist that says, yes, this is interesting to me before anything gets downlinked. Detecting changing regional boundaries. So let's say there are areas on the surface that have these spider-like filaments that are crawling out. And that's sometimes of year they go in, and there's sometimes a year they go out. I don't want to see any spidery filaments. I want to see the edge of that region, and I want to move it over time. And I just want the report to tell me, where's that edge right now? That's another thing Cosmic's being trained to do. And then finally, the global change detection problem. What if I don't even know what I'm looking for? I just want to know if something changed and kind of how much did it change. We can create a detector for something called salience, which is an estimate of, if I showed this to a human scientist that knew something about Mars, where would their eye look and where would their eye ignore? If you can make a functional approximation to salience, then you can store a summarized version of salience for the whole planet. And then the next time you come around, do it again and difference the salience maps and say something changed. There were 3 interesting blobs, now there's 4. Document the 4 and send an alert. That is actually a full planetary detection system for change without judging that change, without storing a single pixel. To do all that, you need precision localization, which ends up being one of the harder problems. So I told you about this sexy system that I'm so excited about. It's in its 3rd year right now to do change detection on Mars. But now let's blow it up in the same way that we're trying to blow up everything in this particular meeting. If there were a system like Cosmic that were in orbit, if it had enough hardware on it to do all that compute and storing all that memory, well, what else could you do while Cosmic is running in the background? And notice, as Cosmic's running in the background, the Highrise scientists are still getting to pull down all the images they want exactly as before. I didn't get in anyone's way. Well, what if we could use it as a comm relay to Earth? Yawn. Everybody does that now, but at one point that was an exciting idea. How about if this is now an orbital compute resource for old or new rovers? What if they start uploading data and analysis requests? And on the night side, when there's no Highrise data, that's what the cosmic system does. Not the cosmic hardware, software itself, but the hardware that it's on. What if this were now, and this is really exciting. I actually think this is exciting as the change detection. I have an onboard compressed knowledge encyclopedia of everything on Mars, specific to change. You can never downlink this, it's too big. But you can upload queries to it. Why don't you tell me all the change detection that happened in this region during this time? It's all sitting there, and then it returns only that tiny little bit. What if you could actually upload your own analysis from the ground? Now you actually have a remote cloud computer, not cloud, a remote compute server with a giant amount of information stuck in it. You can't downlink it ever, but now you can actually say, I want to know things of this size and this arrangement, and I want to know their temporal frequencies. And that information comes down to you without downloading a single instance, unless you request that. What about if now we want to put a bunch of small sats around this thing to analyze something else, but they happen to be spatially arranged around this guy just because you want to use its big, heavy computer? That's the only point that you do that. Or how about during very complex patterns like EDL, so that the next mission doesn't need a big, fat computer for EDL just because it only needs it for 5 minutes, 10 minutes. So what if we permit crafts to exchange analysis requests rather than just data? What if we schedule planetary compute like we schedule comm passes? This is when your data is getting processed on Tuesday at this time by this spaceship. And what if missions gain capabilities when others are nearby and then lose them when they go away? To me, that's what this week, or at least a lot of it, is going to be about. And I think the cosmic is a nice way to show what the limits of autonomy of a single instrument or a single spacecraft could be. This is now talking about what if the whole solar system is kind of acting like that, or at least the system around a planet. Thank you very much.